So let's keep these two concepts in mind as we go through some of the rest of the slides here. And so, just an overview of the approach that we have been using for scene boundary detection. We start with a current shot, which is sort of the middle of a series of shots, and then we look at the temporal neighborhood of our shot in order to find the shot that is sort of most similar to our current shot, and in this way we select our positive key, right, which is a really important thing for the contrastive learning. And then similarly, we select a bunch of negative keys by randomly selecting them from our video corpus, right? And then these positive and negative keys are provided to the contrastive learning algorithm, which then learns the shot encoder. And then this pre-trained shot encoder is then sort of fine-tuned to perform the task of scene boundary detection, where given a pair of adjacent shots, the algorithm determines whether there is a scene boundary there or not, depending on some predefined threshold, right, that we learned during the training. So that's sort of a very high-level overview of how we are actually defining that. And then let me give you some intuition about why did we decide to choose the positive key the way that we did. And this part will be important even in the remaining part of the talk, and I'll come back to it in a different way slightly later, right? So starting with, let's say this is our query shot, right? If we just use some of the more traditional ways of sort of augmenting this shot, like flipping this frame or changing the color space, etc., what you notice is that this type of data augmentation does not really capture any contextual information about this particular shot, right? And so that's not the ideal thing that we should have, right? And so we can start looking more into the temporal aspect to start trying to capture more the temporal context of the shot among its neighborhood shot. Like, for example, we could sort of naively use the previous shot as a positive key for a current shot, or the next shot as a positive key. But as you would notice that the appearance of these previous and next shots can often be completely unrelated to the query shot itself, which is again non-ideal. So essentially what we're looking for is that Goldilocks spot, right? And so we argue that like looking for the most similar shot within the temporal neighborhood of a shot is a good way to do that, which allows you not only the contextual information about a particular shot, but also is similar enough to the appearance of the query shot in order for it to be useful. And that is the fundamental reason why we believe that picking this type of positive key allows us to perform state-of-the-art in terms of sort of scene boundary detection. So now let me share some very few sort of results with all of you. So here is a very typical example of one type of scene boundaries that you often find in movies and TV shows, where essentially before the scene boundary, a completely different place is used for filming, and then after the scene boundary, an entirely different setting is used, right? So as you can see that before the scene boundary was detected, there was a pool and residential home sitting, whereas after the scene boundary, there is sort of this a street fight is actually captured, right? Going through another typical example where a particular actor is captured in one particular setting, and the same actor is captured after the scene boundary in an entirely different setting. So this type of scene boundaries happen often again in long form cinematic content. And then going ahead real quick, for some of our genres, like especially documentary genre, the storyline can be fairly continuous, right? As you can see here, that before the scene boundary, we saw a couple in a hospital setting looking fairly anxious, and then right after that, it's the same hospital, but essentially it's a hallway with a nurse walk, right? So our algorithm is able to successfully detect those types of scene boundaries as well. Just a very small glimpses of the type of results that this method produces. And for any additional more detailed the qualitative and quantitative results, I would very much encourage you to check out our CVPR 2021 paper on this topic. So moving forward, again, for the task of auto tagging and search and retrieval, which is a very important part of overall framework of virtual product placement, I'd like to say more words about how are we looking into the problem of robust cross-modal sort of pre-training, right? And so I'm sure a lot of you, if not all of you, are very, very familiar with methods like CLIP, etc., which essentially what they try to do is try to minimize the similarity between pairs of images and minimize the distance between images and their corresponding captions, while maximizing the distance between all available pairs. And then even though these methods have been extremely effective in the past, they do suffer from two important challenges, and they are really related to the data efficiency and the compute efficiency. Like they're not very data efficient or compute efficient, right? And I would argue that there are two big reasons for that. And the first one is that based on how we are kind of collecting this data at large scale from the web, there is a lot of noise that is present in the caption, for instance, right? So here I'm showing you an example caption, which is sort of the file name, I assume, and has nothing to do with the content of the image, right? And secondly, it really depends on how do we capture the many-to-many correspondences that we often found in very sort of large-scale data set. And because of the way that Clip kind of tries to model these correspondences in a fairly rigid way, the argument is that it's not able to represent these types of many-to-many relationships, and therefore is not able to capture the semantic similarity between the negatives, right? And so the way we kind of try to address this problem at a high level is, we try to, instead of using rigid correspondence, we try to predict soft alignments in order to capture similarity between the negatives in a more robust manner, right? And so the particular framework that we use to do that is sort of knowledge distillation. And as I'm sure a lot of you already know, that the traditional knowledge distillation requires two different models, one for teacher, one for the student, where the predictions made by the teacher model are then used by the student model. And clearly, by using two different models, you do incur different types of costs related to compute and memory, because now you have two models at hand, you have to deal with them. And that can start to actually cost when the size of this model and the scale of the problem grows. And so in order to avoid that, we propose a sort of self-distillation method in a cross-modal setting, where we use the same model for both the teacher as well as the student. And essentially, the sort of the self-distillation part of our loss function, the weight for that sort of keeps growing as the training process increases, such that the student model ends up transforming itself into its own teacher as the course of the training proceeds. And just to give you a prototypical example to highlight the nature of improvements that this type of method can offer us, let's say that our query that we want to use to retrieve from our very large database is a cat lying on top of a chair in the living room, right? And so if you look at the top K results retrieved by using Clip pre-trained model, these are some of the top K results that you will see. And as you can notice that while the Clip algorithm is able to capture the chair and living room aspect of the query really well, it completely misses out on the cat aspect of the query. And here is in comparison, the top K results retrieved by our pre-trained model. And as you can see that it judiciously gives importance to all the three parts of the query. And again, it's just a very sort of a prototypical example to give you a sense or a taste of what type of improvements can you expect from this type of an approach. And for other more detailed results, I would really encourage you to check out our CVPR 2022 paper. Okay, so now let's move on to the more general purpose representation learning problem, because we can't just keep picking individual tasks. We want to do it in a more foundation model way. And so again, the motivation is again sort of focused on Clip and Flamingo and other types of models that have been proposed in the past. But the question is, like, how do we actually do that instead of images, but for long form videos, right? And I would argue that the key challenge is, again, the data augmentation, right? That's really the most important trick, in my opinion, when we are talking about contrastive learning and its application, because like that's still, mostly an open problem, or more work needs to be done at least. And so the key innovation that we are coming in with is that we can use the available movie level information as means for data augmentation to learn a generalizable scene level representation. And the key point that I want you guys to all notice here is that this movie level information is already produced during the natural process of production of these movies and TV episodes. So information like genre or synopsis is already produced in a fairly curated way by the editing and production teams of these long form titles, right? And so essentially, the incremental cost to see that this intuition costs you is virtually zero, because everything that it uses is already available through the natural process of production of these movies. And so, again, at a very high level, the overview is that using this high level, title level metadata, let's say co-watch information or genre, etc., we pick pairs of movies that are thematically similar, right? And then using these pairs of movies, we automatically find what are the right pairs of scenes that we need to put together. And then using these scene pairs, we sort of incorporate them in the scene contrastive learning algorithm. And then once we have learned sort of our encoder, then it's then further fine-tuned to then perform on a wide variety of downstream tasks. And the important thing here to remember is that the guidance that we are providing it is at a very high level of, like, say, 120 minutes, whereas the representation that we are learning is like at fairly more fine-grained level, which is at almost like, let's say, 2 minutes, which is the average, which is around the average length of a general scene, right? So that's sort of the benefit that this approach offers us. And we've tried this method for 14 downstream tasks, and it offers state-of-the-art performance there. And then just to give you some very brief set of visual results. So here are some pairs of scenes that we are able to retrieve that were found to be most similar in various pairs of movies. So say Need for Speed and The Fast and the Furious. And as you can see that purely from a appearance-based perspective, these scenes would look entirely different from each other, but from a thematic or sort of a more kind of abstract perspective, these things are very, very relevant to each other. And here are some bunch of other examples. And you can imagine the types of data labeling related applications that this type of technology can unlock for us. And then again, in the interest of time, I'm going to just quickly skim through it. So again, Men in Black and Men in Black International, etc. That's another example. Here, I'm showing you an example of pairs of similar scenes from a sort of a storm in the ocean type of a setting. Going forward, here's a pair of scenes of two or a few people fighting in some martial arts, etc. way. And then here's two different scenes from two different movies that are capturing Godzilla and sort of that type of story. And as you can see that this method is able to find that. Similarly, in a baseball sort of sports setting, we're able to find very similar, semantically very similar scenes there. Indoor sort of war drama, W or Vice, very different movies in terms of the year of release, etc. But the nature of the content is very, very similar thematically. Then sort of a family pet drama setting where some animals, pet animals are shown. And then just quickly going on, like inside of like a dialogical setting between various people inside of a moving car. And then last but not least, sort of a kind of a dramatic war scenes from two very different movies. And you know, the goal here is to just highly convey, at a high level convey that what type of similar scene pairs that this type of a technology results in. And so for further details, I would very much encourage you to check out our CVPR 2023 paper. You know, go to the ask the authors tough questions and all. Okay, so that's sort of very high level overview of how we're sort of looking at the label efficient learning problem for the broader context of virtual product placement. And then I'm going to be briefly talking about sort of the problem of effectively modeling long-term dependencies within video, right? So as all of you, I'm sure, know that even when we're talking about fairly short form videos, like being able to model the spatiotemporal dependencies among the various key objects within these videos is extremely important for action detection, activity recognition, and so on. And that's all the more important for long form videos, right? Just because the context is by definition longer. And so you know, the importance of this problem is fairly well established. And so more recently, there have been, you know, vision transformers, applied to video have been all the rage, and although they're really promising direction, but in a vanilla sense, they do offer sort of quadratic space-time complexity, and certainly that raises scalability-related challenges, right? And so to address this challenge, obviously there have been several approaches that have been proposed over the last few months and years. And one of the more sort of kind of a very promising one is called Visformer, which offers linear space and time complexity, which is quite often, in my opinion. However, based on our empirical results, we find that the generalizing Visformer, at least in our setting, can be somewhat challenging. And so to address this overall problem, what we are proposing is a novel approach of selective structured state space sequence model, S5. It's a bit of a mouthful, but essentially what it does is makes two important contributions. And the first one is that it uses adaptive mask selection through lightweight mask generation. And what it allows that to do, what that allows us to do is to effectively model long-term spatial temporal dependency. And then the second key contribution here is the long-short mask contrastive learning. And essentially what that allows us to do is to predict longer-term contextual sort of aspect of a video using only a shorter length input video, right? And from those two perspectives, it offers us efficiency in different ways. And then here I'm showing you some summary results of this approach at a high level. So as you can see that our approach can actually offer significant memory advantages compared to all the other approaches, bunch of other approaches that we have compared ourselves with, as well as the number of pre-training samples that are required to offer like a particular level of downstream accuracy. Again, that are quite promising. So again, for further details and a lot more nitty-gritty results, I would really encourage you to check out our CVPR 2023 paper on this topic. Okay, cool. So taking a bit of a sort of step back, so far what I tried to convey to you is in the space of searching for placement opportunities for virtual product placement, content understanding is important, and the two big areas under content understanding that we have been exploring for a while now is how do we perform label efficient learning for a whole bunch of different tasks, including sort of object detection, synchronization, etc., as well as spatial temporal modeling to be able to perform things like action detection, activity recognition, which is all really important for each content understanding. And so in the next few slides, I'd like to change gears a little bit to, okay, now we have, let's say, found these placement opportunities. How do we actually place these 3D or 2D models into these placement opportunities in a way that is so realistic and sort of continues to delight our customers? So, given the long-form cinematic premium nature of our content, it is really important for us to continue to maintain the quality of our content, right? And therefore, we have decided to stick with the more traditional VFX pipeline, right? Because it's a tried and tested path for us. So for in the remaining few slides, I'm going to go give a brief overview of what does that mean and how are we improving it, right? So the traditional VFX pipeline generally consists of a bunch of sub-tasks, right? One of them is compositing, then geo creation, lighting, rotoscoping, and match move, right? So in no particular order, I'm just enumerating them on this slide for you. And in this talk, I'll be talking about a few of them, except that the key challenge that is faced by all of them is that they are all very time consuming and they all are difficult to therefore scale at a web scale level. And so that's really the underlying problem that we're going to try to solve. And so I'm going to be focusing on the two problems of compositing and masking. I'll speak a little bit more about that. And then more specifically, even more sort of precisely, I'm going to be talking about the problem of harmonization and masking. And so let's start with harmonization. So, okay, what's the actual problem for harmonization with? As I'm sure a lot of you know, like basically we have a source image, which is being put on a destination image. And the goal here is to be able to change the appearance of the entire image such that it looks harmonized and natural and sort of well-fitting, right? And so the challenge, this should not surprise you, continuing on with the theme of label efficient learning again, is that in general, for the current state-of-the-art methods, it still requires a lot of labeled training data, which again, as you all know, is fairly hard to collect. And so the key intuition that we're using to solve this is we have a ton of unlabeled data. Can we use that unlabeled data to sort of minimize the need of these labels that we need to train these models? And so, the high level, let's say we have an example image. And so what we do is we synthetically transform this image in a way that we expect the types of transformation that we expect during test setting. So here I'm showing you an example of perturbation of the sort of the overall kind of brightness of this particular image. And then we use these both images with some randomly generated masks to produce a composite image. And the goal of our model is to really try to minimize how does the harmonized image look compared to the example image, right? And the idea here is that if a model can be pre-trained to minimize this difference in a sort of using some synthetically generated noise, then that pre-trained model could be fine-tuned without using as many labeled data. So that's sort of the high-level intuition here. And so we performed a bunch of obviously experiments, and then again here I'm showing you some summary results where on say iHarmony 4 data, we compare our method to a bunch of different state-of-the-art algorithm. I guess in this case it's IS2AM, and as you can see that it is able to meet the current state-of-the-art at around 40% of using the training data, and then if you go all the way to 100%, it sort of fairly comfortably beats the current state-of-the-art, and sort of the y-axis is in dB, so this delta is actually quite substantial. And so, again, for further details, I would encourage you to take a look at our CVPR 2023 paper this year on this topic, and sort of for more results, qualitative and quantitative results. So, moving on to match move, let me start by saying what exactly is match move, because some of you know this from some other names. And so, essentially, match move is camera tracking, and the goal again is that if we can track this camera that was used to capture a scene fairly accurately, then when we insert a virtual object, then the relative motion of the object will align with the relative motion of all the other objects that were there in the scene. And so here, for example, I'm showing you this camera tracking this particular point in the scene. And so the challenge here is that so traditionally, what folks have used to solve the match move problem is to use sort of structure of motion, bundle adjustment type of approaches. But the challenge for cinematic content is that there is actually pretty small motion parallax present in a lot of the scenes of this type of cinematic content. And that makes sense because in order to delight the customer, you don't want the camera to move too much, right? Because otherwise it's too much of a jittery experience. And therefore, generally, the amount of motion of the camera that you observe is fairly limited in this type of data. And so most of the traditional approaches don't actually work as robustly as we would like them to. And so the overview of how we are solving this problem is that instead of implementing deep projection loss, we are actually adding a second part of the loss, which is the depth consistency error. And the way we find this depth is by using a dense depth, pre-trained dense depth estimation model. And as it turns out that by using this depth-based prior, we are actually able to sort of beat this current state-of-the-art by again a large margin. And here I'm showing you some example results that we get from our data. So on the top scene is the input video. On the bottom right, on the bottom left rather, is sort of the back projected set of points here, where the red shows that these points are closer to the camera, and blue shows that they are farther away. And on the third frame, the third video, I'm showing you sort of the reconstructed scene as well as the path, the motion of the camera, the path that the camera took. And as you can see that path is fairly small, right? Which goes back to the point that the motion parallax is actually quite small. And then you can start using this type of technology to start inserting, sort of start doing match moves in a fully hands-off way, and starting to insert sort of basic objects in the scene. And you can see that there are all kinds of different motions that these scenes sort of display, including very small amount of motion to fairly large amount, sort of zoom in, zoom out type of motion, but the algorithm is able to perform fairly well in all of them. And just to give you a few more examples, so this is the scene that I showed you already. I should point out, notice how sort of stable the results are. And the second point I want to just clarify is that a lot of the time you might notice that the occlusion, the virtually placed objects are occluding the objects in the actual scene, and that's because that is a separate part of the pipeline, which is called rotoscoping. Folks who are familiar with the VFX pipeline, I'm sure know this term extremely well. So I'm not talking about rotoscoping in this talk, but yeah, we perform rotoscoping separately in order to make sure that the occlusions and de-occlusions are sort of dealt with appropriately. And so just sketch sort of just quickly showing some more examples. So same is true here. The inserted objects seem extremely stable and aligned with how the rest of the scene is moving. And then one last thing, just to be quick on this. And so again, to find many more results and more details, please take a look at our CVPR 2022 paper on this topic. Okay, so far I have talked mostly about what we call WAD content, or essentially movies and TV shows. But I would argue that the same principles apply for live content, and we focus primarily on live sports, right? And so within the context of match moves specifically, I would argue that that match moves can often be approximated by simple field registration. And the reason for that, as I'm sure you all know, is that in an unconstrained setting, you do need to perform full-on match move, but because you know that the model of the actual field, therefore the problem can be boiled down to, in most cases, like a homography estimation problem. And so we've done quite a bit of work in homography estimation for sports videos, monocular sports videos, and we essentially use a combination of sparsely detected points as well as some dense feature points in order to then combine them to perform field registration. And our method is, last I checked, is still state-of-the-art, I believe. And so here I am showing you some results where on the left is the input video with the back projected model of the field using the homography that we inferred from our method. And then on the right, I'm showing you sort of the field of view that the camera took at that particular instant of time, depending on, based on what our model is inferring for us. And then this method doesn't only work for American football. We actually tried it on US top 5 US tier 1 kind of sports, and it performs quite well in real time using commodity hardware. So yeah. And once you have this type of homography information, you can start looking into really interesting use cases, right? So, for example, in American football, one important use case is yards to go, which at every moment in time tells us, how far is the ball carried there from the touchdown line, and as you can see that you can sort of facilitate these types of use cases very well. Similarly, in the space of soccer, an important use case is like what was the total distance that was covered by a particular player while they were trying to attempt a goal, and also what was their instantaneous speed at any particular point. So as you can see that this player remarkably travels like, I don't know, close to 16 meters, and his instantaneous speed goes all the way to like probably 10 meters per second or something, which is a superhuman number. And so, these types of use cases don't have to be limited to single player. You can start looking into multiplayer sort of use cases as well, where here I'm showing you a very popular foul in soccer. But I'm continuing to call it soccer just to make sure that, I don't, I apologize for that. But yeah, in what is generally called football or soccer, like the player is sort of in front of the second class defense player line, and then he thinks that it's actually goal, but it's not. It's actually an offside foul. And so these are some of the use cases that we use to sort of delight our customers and maximize their engagement with our content. And then last but not least, like pulling this all back to the problem of virtual product placement, right? Like you might be thinking, well, how is it related to virtual product placement exactly? Well, so here I'm showing you a point in a tennis court, and so now with that sort of camera tracking information, what we can start doing is start inserting virtual logos onto the playing field. And here, for example, I'm showing you Amazon, but you can imagine this can be any particular brand, and it can be sort of personalized to a very, very fine grain level of personalization, depending on the interests of a particular viewer or cohort of viewers. And so again, for more in-depth information, I would really encourage you to take a look at our WACRI 2021 paper. And so let me again sort of pop the stack a little bit. So till now, what I've given you a very high-level overview of what is virtual product placement, what are the two key phases of tasks that we need to automate and accelerate in order to scale up the whole system. And then I've talked to you about the various problems that we've tried to address in the space of content understanding that is used for searching of the placement opportunity, and then content constraint, which is then used to actually placing these products in those placement opportunities. And so let me sort of conclude my talk by offering you a few big takeaways from all this this content that I've presented to you, and some various learnings that I had a chance to reflect on over the last few years while sort of doing this project. And so the first one is, as you can see, that like for each one of these tasks, they're time consuming, it's really hard to do it in a manual way at a web scale level. And so super important to focus on how can we automate these technologies in order to scale up the next generation of video experiences that we offer to our customers, right? And so the reason why this is the top level takeaway is because if we put it at the top of our hierarchy, it really influences downstream in terms of how we think about all the problems that sort of we are required to solve in any particular program, but specifically in long-form video context. Right? The second is, as you saw, I'm sure, the criticality of pursuing label-efficient learning, right? Whether you're talking about content understanding space, depending based on how I define it, or the content synthesis phase, as I defined it in the talk, like this problem of requiring large amounts of labels seeps in every which way you look, right? And so it's really, really important to sort of go big on trying to solve this problem. And this is not new, I'm sure, for all of you. It's true for various folks, but particularly in cinematic and long-form live content, this is as true as it is in many of the other spaces. And then sort of last point I want to share with you is really the importance of deep domain expertise, right? So as you saw, while applying, say, contrastive learning in different types of problems, the real breakthrough, if I could use that word, for us came when we reflected back the problem to the particular domain that we're looking at, right? So understanding how the sort of the filmmaking process in terms of how editing works, and how does one shot relate to the next shot in terms of communicating the overall storyline, right? That really enabled us to say, pick the right positive key for scene boundary detection. Similarly, it allowed us to sort of go to the already produced sort of title level information like genre and synopsis in order to sort of start taking steps toward sort of a foundation model for movie understanding and so on. So I just wanted to re-emphasize again, somewhat stating the obvious here. They're like, yes, approaches like, semi-supervised, self-supervised learning are extremely promising and extremely powerful, but it's still, where we are today, it's still fairly important to be able to be aware of the domain, sort of the domain-specific details in order to use these technologies effectively in practice. And so with that in mind, thank you for listening and thank you for the invitation, and I'd love to open it up for discussion and so forth.
Thank you. Any questions, please?
First of all, thank you so much for the great presentation. I'm more interested on the first part of the talk. Curious to know, like, for negative sampling of trusted learning, it's a very tough problem. What's the rationale behind defining the positive variable? Is it just the location of the norm? That it's really part of the break, it's an assumption. How can you think about that?
Great question. Thanks for asking. We've been thinking about that. Right, so yeah, it's a combination of the things that you sort of think. So let's start with what's happening in this piece of work, right? As I mentioned, because of the editorial aspect of how folks film a scene, right? There is some amount of continuity and the way that these shots are actually captured. So I think the lowest hanging fruit for us was to just start with the shot, look to the left, look to the right, in sort of a predefined neighborhood sense, and then pick the nearest neighbor in terms of predefined similarity. We did try picking top two or like the second from the top or repeating this thing, but didn't really sort of change the results too much, so we stuck. Now, that said, I think there is a big opportunity here, right? Because as you correctly noticed that the scope at which we are limiting ourselves is very, very small, right? So yeah, of course, we should expand that and extend that to, you know, many other sort of maybe cross title positive key selection and so on and so forth, right? The one thing that I would kind of highlight here is that we should be aware of the computational cost that comes with that. So so it's non-trivial to increase the scope kind of, you know, in a sort of willy-nilly way. So yeah, just keeping that in mind.
Have you explored, this is a sort of curiosity. Have you explored with any like non-parametric approach to learn transformations?
No, we have not. No. The ones that we have explored are some of the more traditional kind of augmentation approaches, like as I was mentioning, jittering, rotation, and so on, and changing of color.
More questions, please. Okay, so thank you again. Patrick.
Okay. Great. Thank you.
So now, I'll take a, yeah, let's take a 5 minutes recess for us to connect and we'll start over. This was great. I think you should give this book to our group. I love it. It will inspire them. Okay. To see that they can make this kind of papers and this kind of work. Because, yeah, well, we should talk about it. Yeah, that was great. Yeah. Yeah. So let's connect.
Yes.
Nice.
Nice to meet you. Thank you.
Yeah, that's nice. So let's connect and you have the Zoom and then we can actually start the broadcast because until now we didn't broadcast anything. Because I didn't know how to connect, but now I was told how to do things.
So I received 2 links, but I think only one of them is working.
No, the second one. Yeah, this one.
This one. Okay.
Yeah, so
okay,
let's
wait.
connect.
So just here.
Yeah. Yeah. And then, okay, are you on? What does it say?
So I'm waiting. It's like
No, no.
I'm in the waiting room.
You're in the waiting room.
Yeah.
Admit all.
Okay, now it's joining.
Joining.
Okay.
And now can you share?
Yes.
Can you? Because I didn't allow people to
Yeah,
share.
looks like I can.
Share. This is old. Hi, old.
No.
No, okay. So I will allow you to share screen. Please share your screen. Okay.
And it should be this one.
And I will start the recording, okay? So in a few minutes, I'll just start the recording. All right, this is good. And you are muted, so
Yeah,
have a
I
look.
have to unmute first.
Yeah. Also, maybe I have to unmute because probably it comes from here. But let's do both. Yeah, I have. Yeah, because I'm not sure who is muted. How do I
Oh, I think you should enable me to share audio.
Okay, so let's see how we do that. Font is that. How we, this is you?
Yeah.
Ask to unmute.
Okay. Okay.
Yeah. So now we're on.
Okay.
Yeah, great.
Let's
Okay.
again, see if it goes. Okay, so that should work.
Yeah. Okay, so luckily for
Okay, let's wait for I won't be able to attend the workshop. I need to have we have a workshop parallel, and since it was meant to be 7 in the morning, I had to say no, it's not. I wasn't able to reschedule the next parallel. Interesting. To get rid of that. Not sure how.
Do you have your do you have your resume because someone didn't send it?
I sent something.
Yeah, if you sent, I have it. Yeah, that was not easy. Yeah, how do I get rid of this? I will go like that.
You are connected from your laptop.
Yes, but I want to get rid of that bar. I'm not sure how that's done. Maybe
you can
it's
move it around.
this one. Yeah.
Okay, okay.
Everybody can see it.
Okay, so now we'll move on to our next talk. Our talk is by Professor Antonio Furnari. Antonio Furnari is an assistant professor at the University of Catania. He received a PhD degree in mathematical and computer science in 2017 from the same institute. He has been working on first-person egocentric computer vision since 2014, and is part of the EPIC Kitchens and Ego 4D teams. His research focuses on understanding human activity and future intent from geocentric videos. Thank you for coming.
So hello everybody, and thank you for inviting me today. So title of today's talk is towards a fine-grained understanding of human behavior with egocentric vision. So I'd like to spend a few slides to tell you why I think this is important to this workshop, why this topic is relevant to the workshop. Let's see if this works. Okay, I'll use the old-fashioned way. I probably didn't have. All right, so understanding customer behavior is probably one of the most relevant aspects when you think of applying computer vision to retail stores. And there are many ways to understand customer behavior, and there have been many ways for a long time. But for sure, one of the things that come to mind is just to place a camera. Maybe you hung it to the wall or to the ceiling, and you start collecting images, videos of people going around in a supermarket and interacting with objects. And this already allows you to deploy some interesting services such as localizing, tracking, re-identifying people, understanding how they move, understanding how they interact with the shelf, which is very valuable for managers, for instance. But a shortcoming of this approach is that the granularity of behavior understanding that you can reach is kind of limited. Instead, think of what you could achieve if you could if you could equip, for instance, customers with some kind of wearable device, like wearable camera, smart glasses with a wearable camera. Well, you could get a fine-grained understanding of their interactions with the world, which could be in some way complementary to what you get with a fixed camera. And also, you can also provide additional services through the wearable device. So one of the questions is, okay, fine-grained understanding is good. Why wearable cameras? And is there another way to do that? Why cannot I do that with, for instance, fixed cameras? So if we want to monitor somebody doing something with fixed cameras, we can place a camera in some position and start collecting some useful information. So for instance, in this case, we see from this view that there is a kitchen and there is somebody probably doing something in the kitchen. We can imagine it's cooking or cleaning or something related to that environment. But of course, I mean, it's hard to get a perspective on what objects the person is manipulating and what they're doing at a fine-grained level. So we could place another fixed cameras if we want to stay in that realm of fixed cameras. And for instance, here we have a top view. So maybe it's easier to understand where people move, to track them, but still we don't get a clear view on the objects. And we can think of installing a third camera. And now this gets better, but if the person moves and goes somewhere else, then we have to switch camera. So the point is this approach allows you to collect useful information, but the information that you get depends on human activity and on camera positioning. So, well, if you want to solve the problem with cameras, you need to place a lot of them, and then also to orchestrate all the information and changing from one camera to another, depending also on the activity. But if we place a camera on the head of the person, so what we automatically get is a privileged view on the interactions that the person has with the different objects. Of course, we're going to miss something maybe about the environment, but for sure, if our concern is to understand how people interact with the world at the object level, we always see hands and objects very clearly from this kind of view. And also, as I was saying before, if you place a wearable camera on smart glasses, then you can use smart glasses to provide even other services. So how do we get back to our retail store? Well, think of what you could do if you could add wearable cameras on top of customers and get this privileged view. Then services which are automatically enabled are, for instance, recognizing objects and interactions, understanding customer behavior, anticipating customer behavior, so predicting what the customer is going to do, localizing users that's still possible, allowing them to navigate and to reach parts of the environment in a better way, and also provide personalized recommendation, because by looking at the world from their point of view, you can understand what they are interested in. And so the question is, are we there yet? So do we have that technology today? And I had to put a little disclaimer here. I feel a bit bad about that, but there is no retail applications in this presentation. And this is probably because we are not there yet. So, in the rest of this presentation, I'd like to explain work that we have been doing as a lab and as a community in these fields that I think can enable this kind of application, even if we are not there yet. So the answer is, we get there when we get there. All right, so the rest of the presentation is divided into two parts. We have a first part in which I like to talk about a relevant topic of understanding human behavior as this fine-grained, which is understanding the present, so understanding the interaction that the person has with the objects. And in the second part, instead, we have another relevant topic, which is understanding and anticipating the interactions with environment. So understanding the present and understanding the future. But let's start with the first topic. So if we want to understand human-object interactions in any environment, for instance, a retail store is one of the possible applications, then what are the questions that we could ask and try to answer about that? For instance, what's the action? So what is the person doing here? Is the person taking a package, or is the person putting it back? Where are the hands, which give you information on what the interaction is, or what objects are being grabbed or not? Where are the objects present in the scene? Which of these objects are being actively manipulated by the person, and what are the classes of the object? These are classical questions that you can try to answer and that the community has been focusing on. And how do you solve that? Well, we all know in this room what's the magic ingredient of that. You need the data. And you don't need just any data. I mean, you could do something with, I don't know, just object detectors, but you need data which captures the world from the user's perspective. So you need egocentric data. If we jump back to 2018, this was the situation of datasets of egocentric videos in 2018. So there were some datasets, but most of them were very narrow. 2018, for instance, the kinetic dataset was already there for video understanding. And I mean, the community was not at the level. We didn't have enough data. And in this context, a new dataset, which is the Epic Kitchens dataset, came out, which was, I think, in some sense, a good moment for the community of egocentric vision. And the Epic Kitchens project is a joint effort between three universities: University of Bristol, of Toronto, and University of Catania. And you can see the faces and the names of people involved in the first work in 2018. And what we did there, so the idea was, let's try to collect data which tell us something about visual perception of people. And of course, this is not easy because While for kinetics, for instance, you could crawl data from the web, that was not easy to do with egocentric vision. So the easiest thing that we could come up with was, let's try to ask guys to collect their data. But it's very hard to ask people to wear a GoPro and go about in their lives and maybe go to their homes, sensitive spaces, bedrooms, bathrooms, and collect everything. So we asked them to collect visual information on what they did in their kitchens for 3 days. So we asked 32 people to collect videos in their kitchen. So we have 32 separate spaces in these data sets. And we collected 55 hours of video, which was already a good number at the time. And it's 11.5 million frames in total. And this is completely unscripted, meaning that we didn't ask subjects to collect specific actions, but we wanted to know what they would do in the kitchen. And the kitchen was chosen because you have a lot of interactions with objects, of course. We collected using GoPro, so the video is fairly good quality. And then we labeled with about 500,000 object annotations and 40,000 action segments. There is beginning and end of an action and a label for the action. And as a result, the dataset is very diverse. And you can see also videos such as this one. Which is exactly what we want to capture. So we want to have data which tell us how people, even how people screw up in their lives, let's say, so how people interact with the objects in a natural way. So then once you have this data, you have to provide annotations for this data. And of course, you want to get to semantics, and you have the chicken egg problem. So what do? Ideally, I mean, the way we are used to do it is, let's start from the taxonomy and then let's collect the data. But this is not a good approach in this case, because we want the data to be naturalistic, to have these natural interactions. So instead, we had to adopt a bottom-up approach in which the taxonomy actually comes from observing the data. So we, after video acquisition, we asked the data collector, so the subjects collecting the videos, to comment on the videos, so to talk over the video, explaining what they were doing. And then we transcribed those, and from these narrations and points in time, we labeled action segments that explain that tells you where each action starts and when it ends. And then we did some semantic parsing to attach a verb noun-based representation. So we have actions such as cut onion, and you have a video clip for that, and turn off tap and dry cup. And this is a gist of the kind of annotations we had in the first version. So a timeline with narrations, action segments, and object bounding boxes. And we extended these data sets a few years after that with Epic Kitchens 100. We extended the data sets in different ways: number of hours, number of kitchens, number of videos, number of action segments, classes, and we also rationalize a little bit the verb and noun taxonomy. So we have less of them, but they are more focused. And we also provide train, validation, and test splits. And also the annotation pipeline was improved in this extended version of the dataset, providing an interface for people to click on a specific point in the video in which they believe there is something interesting to narrate about, and add an audio comment. And these allow us to get more precise narrations and also denser narrations. And Epic Kitchens is a dataset and a community that keeps growing over time. So there are many follow-ups work. And in one of these, we focused on also on visual object tracking. So the ability to track objects is a very useful one, but it has been always investigated in the context of fixed cameras. Well, not just fixed cameras, even moving cameras, but not cameras worn by a person, so which give you this different perspective. So we investigated that. We annotated for object tracking some sequences of Epic Kitchens, and then we ran lots of state-of-the-art trackers on that. You can see the results here. So you see on the left the video with the ground truth in white, On the right, you see the ground truth plus the results of different trackers. And as you can see, it doesn't, I mean, current trackers do not work very well. So this was our first insight from this paper. So we need to, the community to focus on this kind of problem. And we also tested how good is to use a tracker inside an egocentric vision pipeline. So in this case, the task was to understand user-object interaction, which is usually based on an object detector. And we try to replace the object detector with a tracker. And we saw that better trackers lead to better performance. So this suggests that tracking is an interesting problem, which can be useful for downstream tasks as well. But apart from tracking in general, what we wanted to do with this data set is also to push the community to investigate problems that we believe are interesting in this domain. And so through the years, we defined a series of challenges and we asked people to engage with the challenges. And this is the current list of challenges. Some of them are newer, some of them are older, some of them disappeared at some point. So this is not the full list of all the challenges ever run, but this is the current list of challenges. And we want to push the community to work on tasks such as action recognition, detection, anticipation, domain adaptation, or tracking, and so on. And to do that, we started organizing since 2019 at CVPR a series of workshops where we announce the challenge winners. And we have a technical report each year which summarizes the advancement of the community on these tasks. So we have reports up until this year, and this is coming soon. So we were very, very satisfied of these efforts, and but maybe it was not enough. So the real question was, can we scale beyond collecting images and videos of people interacting with the world? Yes, but in their own kitchen. So with this specific and narrow scenario. And this is in this moment when we had this question in mind, we had the chance to be parts of this bigger project, Ego4D, which is the consortium of 13 universities, and resulted in last year in the publication of a paper at CVPR with 84 authors. So Ego4D, the idea is to scale up this process and collect a data set which better summarizes the visual perception of people in different environments, not just kitchens, but everyday environments, outdoors, indoors, their daily activities, but even what they do at work, if they walk the dog outside, everything that can come to mind. And the results is an evolving data set. These were the statistics when we published the data set. Now I'm sure there is more hours and more subjects, but this is the scale of data sets, about 855 subjects and videos collected in 74 locations, nine different countries, about 3,000 hours. And we have 3D scans of the environments for some of the videos. We have audio in almost all of the videos, and we have gaze for a subset of the videos. And as we did with Epic Kitchens, we also in this case, we suggested a series of challenges which we believe are important, like, and we created these five different benchmarks. Episodic memory, these are challenges and tasks aimed at trying to understand what happened and remember what happened in the past. So creating systems which can answer questions such as, where did I leave my key? Where should I look? Hand-object interactions, so understanding where the hands are and which objects they are interacting with. Audio-visual digitization, so modeling people talking and objects emitting sounds. Social interactions, understanding how people interact with each other, and forecasting, so predicting the future, what the person is going to do in the future, which object they are touching, and what is the next sequence of actions, or where their hands are going to move in the environment. And also in this case, we proposed a series of workshops. So since 2022 at CVPR, we had, this year at CVPR, we have the third iteration of the workshop. And again, we announced challenge winners at these workshops. And the idea is, again, to push the community to work on fundamental projects which can advance knowledge in these fields. But these efforts aim to work towards fundamental tasks But in most applications, you also should focus on the specific domain in which you're working. So many applications, and I think retail is maybe one of these fields, you can make a closed word assumption. So you can make assumption on which objects are going to appear in the scene, and maybe you can create a taxonomy of things you are interested in, which changes depending on the domain. And examples of these scenarios that we have been interested in as a lab are, for instance, retail stores, cultural sites, and industrial environments. And in particular, with respect to industrial environments, we also focused on collecting data which can allow us to understand the perception of people while taking procedural activities such as assembling something or working on an assembly line. But since it's very hard to collect data and in real industrial environments because of privacy, because of the safety of the workers who should collect the data, we came up with the idea of collecting a data set of people assembling a toy model. And this is a collaboration also with University of Hertfordshire and a local company, Xenia Document Management. So we asked 20 subjects to collect videos where they were assembling a toy model of a motorbike, which is a procedural activity. And also, since wearable devices such as smart glasses tend to be very naturally multimodal acquisition devices, meaning that you not only acquire RGB videos, but also gaze to understand where people are looking, what people are looking at in the scene, or also depth information. Then we collected all these kind of signals to try to have a multimodal data set. And we then labeled data with different annotations which can allow us to understand the past and the present, let's say, and the future. So we annotated the starting and end time of each action, and then the positions of hands and manipulated objects. And then we tracked these bounding boxes back before the beginning of the action, so that we can also try to understand what's going to happen in the future. So I know that a given object is not being manipulated now, but it will be touched at some point in the future. These are the kind of labels that we have. And using this label, we can investigate tasks such as multimodal action recognition, action anticipation, active object detection, and next active object prediction. And in particular, and this is a task we are working on at the moment, is egocentric human-object interaction detection. And the idea here is that you want to understand where are the hands, which objects are being manipulated, and optionally also understand what is the action that you are performing. But to tackle these kind of tasks, you usually need a lot of data. We have been talking about data for a while at this point. This is good if you want to solve fundamental tasks. But when you come to the specific narrow scenario in which you have a specific taxonomy, maybe it is not sufficient to have this general domain, and you need to adapt your method to the environment that you're choosing. And this means that you need to at least to fine tune. And to fine tune, you need in-domain data. So we have this problem that we can have a very large data set, but then in the end, if you want your system to work in a specific environment, you're still back at collecting at least some data in that environment and labeling it, which is expensive. So we are investigating what we can do if we use synthetic data. So what if we could learn the real thing in simulation before actually maybe then also acquiring a few some data, some real data, but just a small set to fine tune. So try to do most of the learning in simulation. And we have been working on this in the past few years. These are the faces and names of people involved in this project. And what we propose is to follow this pipeline. So you take a specific environment in which you want your system to work, and the objects that you want your system to be aware of, and you create a digital twin of your environment. So you collect a 3D model of the environment with a 3D scanner and 3D models of the objects. And then we developed an interaction simulation tool using Unity 3D. So we leveraged all the assets that we could from the the game industry, because what we want is a very good video game in which you can simulate interactions with objects. And by using this tool, we could generate a data set of interactions, of hands of people, of short videos of people touching buttons and taking grabbing objects. And the good thing is that since this is all done in simulation, you can get the ground truth for free. So we could get object bounding boxes, contact states that you measure. You just measure if there is actually a contact between the digital hand and the digital object. But we could also acquire the simulated depth and also masks around the objects. So we gather these data sets, and we also collected another data sets of real images in the same environment with the same object to check if actually you can generalize to real data after you train on synthetic one, because of course the goal is your system to work in the real world. And we come up with an architecture which is based on previous work, but which also adds some multimodal processing, because now we have all these multimodal information that you have at training time. You won't have it at test time, but you still can use it for regular eyes. So we have an input video, an input image. Then we extract some features with a backbone, and then we have an object detector branch which recognizes all the objects. And we have a mask branch and a depth branch, which are responsible for processing the masks obtained from the ground truth and the depth. And these are actually predicting from the input image, so that then we can train to predict at training time. And then at test time, we have the prediction on the real data. And then we try to understand what is the relationship between each object and each hand, so that we know if a hand is in contact with a given object. And without delving too much into the details, these are some insights from the results. So if you use only the real data that we collected and you train the model from scratch, well, not exactly from scratch, you have the usual pre-training that are not in domain. So for instance, you have pre-trained on Coco or ImageNet, but not in domain data. And then you fine tune with the real data, you get, you get very poor performance, like 17% MAP. If you consider a class agnostic setup, so the idea is, one comment could be, okay, you don't really need in-domain data. You just train with lots of out-domain data, and your method will generalize eventually. But if you actually take this approach, so we use the class agnostic algorithm, which tells you, you are in contact with an object, but I don't know what the class is because I don't know anything about the domain. And then we train an in-domain object detector, and we try to fuse these two. We have an improvement, but it's by 3 percentage points. And then when we train just on synthetic data, so not other external data, just the synthetic data, but this is in domain, we already are beating all the two models on real data. Then once you fine tune the model trained on synthetic data with real data, then you can get a large boost. There are other techniques that we have not investigated yet, like domain adaptation. Of course, they can even allow you to use unlabeled data rather than labeled data. And then if you add also the synthetic, the multimodal connection, we are still investigating this, but you can already get a small boost with the multimodal data available only at training time, only in simulation, even with naive techniques. And these are some qualitative examples. So what we get on real data after following this setup. Okay, and now I'd like to go to the second part of the talk in which we talk about anticipating human-object interaction. So if the first part was on trying to understand the present, and there is still a lot of things to do, but something that is also interesting for understanding the behavior of a person is anticipating the future. So what are the kind of questions that you can try to answer in this case? Maybe again, what is the action? But in this case, what is the next action? So if I see an image like this, what is the person going to do? For instance, which object the person is going to pick? What is the next active object? So localize the next object that the person is going to interact with. And what is the class of the next active object, and when the interaction is going to take place? So in how many seconds you're going to touch that? And one of the the application scenarios that we always have in mind is to improve people's safety. For instance, in a factory, if a worker is going to touch the wrong button, you would like to understand that maybe a few instances before, maybe 1 second before, to give an alert or to do something about that. And we started to work on this topic a few years ago in 2016, and this is a collaboration with University of Texas at Austin. And the first way we formalized our problem was the following one. So let's say we have a person moving in an environment, for instance, in their own kitchen. As the person moves towards an object, so let's say the person wants to open the fridge, we should be able to understand from the motion of the person in the environment what is the next object the person is going to interact with. And we call this the next active object. So at the time, we investigated how you can do that with motion. So the idea is, as you go towards an object, the motion should tell you something about what object you are interested in. But since it's not trivial to track the ego motion of a person from egocentric views, we actually use the motion of the bounding box of an object as a proxy for that. So the bounding box of the object will move in the egocentric view frame in a way that is a proxy for a human motion. And we come up with this pipeline in which you have an input video, you detect all the objects you are interested in, and then you track these objects, you extract some trajectory descriptors from the trajectories, and then you classify the trajectories in two classes. This is either a next active object or this is a passive object. I'm not going to interact with it. And so in the end, you can have prediction. So in red, you see the ground truth. In green, you see your prediction for what a next active object is. And in blue, you see a prediction of what, an object is there, but probably the person is not interested in it. This is a video of some success examples. So it is not perfect. It doesn't work always, but already by just looking at motion, you can get some cases in which it's clear that the person is moving towards the object. But this was, at the time, very limited by the lack of any semantic reasoning inside. And it also was a complex task for the time. Fast RCN was already there, but already training an object detector was hard. So putting video and an object detector together was a bit prohibitive at the time. So when we got to work on Epic Kitchens and we had this idea of let's define challenges that we want people to engage with, this was a bit too complex. So we thought, how can we define something that can be easier for people to tackle as a task? And so we come up with this definition of egocentric action anticipation task. Well, it was not that novel. There were other similar definitions, but we defined this within the data set. And the idea is that you have a video, you have an action happening at some timestamp, and the task is defined as follows. So you sample a video before the beginning of the action, 1 second before, and you can take a longer video if you want. So you can look as far as you want in the past. You are not supposed to look at this at what happens in that 1 second gap, because you still want your prediction to be useful. So to be made at least 1 second before the beginning of the action. And then by observing this video of the past and never observing the video of the future, you want your model to predict the future action. For instance, in this case, the next action is take plate, and this is going to happen in 1 second. And of course, this take plate action was never observed by the model. And we also proposed a model to try to tackle that, which was based on LSTMs. I think transformers were already there, but not so cool yet. So that's why we used LSTMs. I guess this could also be revised with transformers. But the idea is that we have two models, an encoder and a decoder, as you usually have in language models. And the idea is that the encoder will try to create a semantic summary of what has been seen so far. And at each time step, the decoder will take over and also try to anticipate what will happen in the future. So we have these two models that we called a rolling LSTM and an unrolling LSTM, which is unrolled to predict the future. And the model we provided is multimodal, and it processes RGB frames, optical flow features, and also object-based features. And then the way we fuse that is with an adaptive mechanism. So the idea is that you can fuse these signals from these three modalities in a constant way, but maybe in some cases the object vector is failing, or there is no object and you should just use context, or there is not a lot of motion and so you should just use mostly RGB. So we thought of an adaptive way to merge the modalities. And let's say you have 2 branches. In our final architecture, we have 3, but we also have experiments with more branches. You can add different modalities. We take the encodings of the 2 encoders, the rolling LSTMs. We concatenate those. We propagate them through a network which outputs 2 real numbers. Then you normalize the 2 real numbers with a softmax so that they sum to 1, and you use these numbers to get a weighted average of the logits. And so in the end, you have a late fusion, which depends on the given input. We train the single streams separately, and then we fine tune end to end because this is fully differentiable. And these are some examples of our model at work. So what you see in this video is at the center, you have the input video, and then in the top, you have a timeline. You have a first stage in which the model is observing but not making any prediction. And then during the anticipation stage, the one in blue, you have a prediction every 0.25 seconds because our model can also refine predictions through time. Of course, when you are very far from the image, it's hard to get what is going to happen, but you can refine with time. In red, you see the action, which is never observed. And on the right, you see the list, the ranked list of the actions. The first 5 are highlighted because these are, so when we have a correct prediction in the first 5, we say this is a successful anticipation. And you see in bold the ground truth one. So let's see one example. For instance, in this case, the future action is empty bottle, and we are predicting, apart from empty bottle, also closed tap, dry hand, wash bottle. So these kind of models, even if they are trained to forecast the future, they can actually get an understanding of what actions are plausible to meet at that point. And this is based on the analysis of the objects which are around. And this is shown in the bottom right corner, in which you have optical flow, RGB, and also the objects in green. And we further extended this idea of predicting the future with some more practical implications. Again, going back from the theory of we want to solve a fundamental problem to this actually needs to work in real life. So we noted that our nice rolling LSTM took about 800 milliseconds to anticipate what's going to happen in 1 second. So we thought there's something wrong because if you have, so you need, let's say the outputs of your model will be used by some downstream task. And if you want to know what's gonna happen in 1 second, then you need to have that prediction at least 1 second before the action happens, not 200 milliseconds before. So the classic setup of action anticipation and how you evaluate these models is you have a video, then you have an anticipation time, and then you have your future unobserved action. So you are just observing the video, and usually you assume that your runtime is negligible, and you are observing a video, and then you are making a prediction, and this prediction will be available 1 second before the beginning of the action. But actually, what's happening is that you have a runtime, and so your prediction in the real world will not be available 1 second before, but it will be available 1 second minus your runtime before the beginning of the action. And so we call this effective anticipation time, which is actually compressed. And the big problem with that is that if you evaluate models that have different runtimes, so they are actually evaluated on different effective anticipation time. So they are, let's say, they are useful in different ways. You can have a very big model, but if it takes 2 seconds, it's not an anticipation task anymore. It's a recognition task because you are getting your prediction when the action is actually ongoing. So instead, how do you fix that? One easy way to perform a benchmark of diverse models with different runtimes, which is a bit more fair, is to shift the observed video by the runtime. So the trade here is you have a slow model, maybe it's a better model, but you need to allow for the runtime. So you need to shift back and observe an older video. And of course, there is a trade-off there because you can have a very heavy model, but then you will have to look farther in the past and the prediction will be more difficult. And we made a benchmark, and of course, I'll show you the results in a slide, but of course, the bigger your model and the more it is penalized. So we thought, how do we get effective and smaller models? And one way to do that is to scale your model in some way. So we took a simple R2 plus 1D network, 3D network for a video understanding, and we checked what happened if you, rather than taking an input which is full resolution input, you take a small resolution input. This is an easy way to have a smaller runtime, even if you have the same model. And as you can see in these slides, you see that runtime goes down, and the buffer size, so the size of the buffer that you need to store the video, goes down, but also performance tend to go down as you decrease the resolution. So how do you fix that? We try to use knowledge distillation, and we benchmarked a little bit what happened if you try to distill knowledge from some other source, so that the model, even if the resolution is smaller, can still learn. And we tried the usual big to small distillation. So the usual, you take a big model and you try to distill into something small, but this actually didn't work very well. What worked was instead to try to distill information from the future to the past. So you take a video, you take a pair of clip, and you take a past video clip and a future video clip, which are paired. Then you extract features with your model on the past observation to anticipate the future. And of course, if you have labels, you can train this branch to predict the future. And then to regularize this training, we also took an action recognition model, which is frozen. So this was trained for recognition, and we extract features from the future as well. And then we have a knowledge distillation loss, which tries to regularize. We have ablations in the paper, but in general, these tend to work very well and improves performance. So what we found is that we summarize our findings in this image. You see the triangles on the left are the models when they are evaluated with a standard approach, so without shifting the observation back. But they are plotted not just with respect to performance on the y-axis, but also with respect to the effective anticipation time on the x-axis. So the models which are on the left are actually the least effective because they have a smaller anticipation time. Then the circles tells you what happens if you evaluate the same models using the streaming evaluation protocol that we propose, and the dashed lines make this connection between the same models evaluated in the two ways. And now, as you can see, the effective anticipation time is restored, is 1 second, but you see that models which are heavier, like the one on the top left, gets very, very bad when they are evaluated in this way. So then what we, which is what you observe here. So that what we also observed is that if you take lightweight models, and we have a few of them, and you perform knowledge distillation, that you push those models from the bottom to the top, and since they have a small runtime, then they are less penalized when you apply the streaming evaluation protocol, and overall these are better than the very, very heavy model, and they also can run at a higher frame rate, which is also a good feature. And the next thing I want to talk about is an effort that we had to try to merge the first two tasks that you saw. So next active object prediction, no semantics, but it's grounded. And the second task is action anticipation, a lot of semantics, but it's ungrounded. But in many cases, especially when you want to make decisions which are explainable, you want your decision to be as grounded as possible. So it would be nice to say, this is the next action. You're going to take that glass, but it's not just take glass and hypothetic glass is like, this is the glass, this is the bottle. So we try to merge these two definitions in and propose this as one of the tasks and challenges of the Ego4D datasets with the task that we termed short-term object interaction anticipation. So this is the idea. You have a video, you take the last frame of the input video. This is a high resolution frame, which is the last one of the input video. And you want to anticipate what is the next action, but you also want to localize the object. So the task is find a bounding box around the next active object, but also attach to this bounding box the action, the next action, So for instance, a verb such as take and the time to contact. So in how many seconds you're going to touch, you're going to take, in this case, their object. And we also proposed an architecture which tries to tackle that by merging two things which are important to achieve this goal. You need to process a high resolution image because a low resolution image would not be enough to detect objects reliably. And then you need a low resolution video to do video processing. Low resolution because, well, you could try to do video processing at the high resolution. Good luck with that, but it's very, very expensive. So you need a low resolution. And usually the first baseline we had for this was you have two separate models, and for that you train separately, and then you try to put the results together. Instead, we propose to have a unified backbone. So we have a 2D backbone which processes the high resolution image, and we extract features from there. And at the same time, we extract features with a 3D backbone on the low resolution video, and then we try to merge these features. And to do that, we upsample the 3D features. We temporarily pool the 3D features so that now they become 2D features, which still have some notion of time. And then we fuse these features with the 2D features, and we apply a feature pyramid layer. So at the end of the process, you still have 2D features, which should have inside both knowledge of 2D, so high resolution image and objects, and 3D, so actions which are going on in the video. And to these feature pyramids, we attach a prediction head, which is based on faster RCNN. So we have a region proposal network, which tells you what are the proposed object regions. With Royal Line, we extract local features. We also extract global features by average pooling the feature pyramid features. And this is good to obtain an understanding of what the scene is telling you about some kind of prior of what the next action could be. So for instance, if there is a sink in front of you, even before detecting objects, you can understand that probably the next action is going to have something to do with water or with the tap. And then we fuse the local and global features with a residual connection. And after that, we predict for each of these boxes the noun, the verb, and the time to contact. And this is the kind of output that you get. So in red, you see the ground truth. For instance, for the image on the left, the ground truth is take playing cards, and in green, you have our predictions. Also, in this case, even if you train to anticipate the next object, the model will try to make predictions on something that's that is not in the ground truth. For instance, in this case, one of the predictions is take food in about 2 seconds, which is still a reasonable prediction. And on the right, you see that the next action is take food, and the model in this case can anticipate take food. And this model was ranked first in the challenge last year, and this year it was the baseline of this year challenge, and it's not top ranked anymore. But the interesting thing is that the winners based their code base on our code base, which is exactly what we wanted. So we wanted to provide an improved baseline which can be hackable, because if you have an idea, rather than training different components and putting them together, then you can change the head, change some small detail, and then fine tune. And we have code for that that is publicly available, and this is based on detection 2. So that's, well, it's not based on detection 2, but its organization is very similar. Let's say it's copied from detection 2, if I can say that. But like the organization is in a way that you can hack it very, very easily. And before concluding the talk, I'd like just to spend a few words on another project that we have at our lab. In 2021, June 2021, so about 2 years ago, we should probably celebrate, we funded a spin-off, which is called RetailVision. It's been funded by me, by Professor Giovanni Maria Farinella, and by Francesco Ragusa, who at the time was a PhD student. Now he's, I think it would translate to research associate. And we also had a local company, Xenia, who funded and supports the spin-off. Well, what's the idea? The idea is to bring our academic knowledge to real applications which have something to do with mobile devices, and in particular with wearable devices. And we're working towards 3 lines, 3 products, which are Nairobi, an indoor visual navigation system. And I'll show you a quick demo of this in a second. and Naomi, and a human object understanding, interaction understanding system, and Hero, a human machine interaction system. And this is a demo of what we are doing with Nairobi, which is probably the most mature product so far. This is an indoor navigator. So the idea is while in outdoors, you can use GPS to localize yourself. Indoors, this is not doable because the GPS signal cannot penetrate indoors. And so by using computer vision, we can localize the person, and by using augmented reality, we can show the directions directly on the screen of the smartphone. And this is the case on the right. And instead on the left, you have a wearable device. Well, a moment ago, you could see a wearable device, this one. So we are developing this kind of solutions. We believe that there is still a lot of fundamental work to be done in the field of egocentric vision, but some of the things that have been done can already be translated to real products, and we are actively working for that. And again, sorry for not having any retail applications, but I believe this is very relevant, and we need to push the technology at a fundamental level so that then applications are easy and can be done as a top layer. And thank you for your attention. This completes my talk, and I'm happy to take questions.
Questions, please. So I have a question. So this actually relates quite directly to Oculus and this kind of devices, the new Apple device of that.
Yeah.
Although that's a little bit different. Like the Google Glass and all of this kind
Yeah.
of hardware. So are you working on connecting this kind of techniques or technologies into those kind of products? I mean, can you connect this to Oculus? Because this seems like the thing they really want to get people to use. I mean, that's the
So ideally, yes. In practice, we are computer scientists. We are focusing on software, on algorithms that can be as general as possible so that you can deploy them anywhere. So the case of Oculus, it's mainly a VR setting. I know, but I know that there are I don't know the details, but I know that there are versions such as, for instance, also the Apple device is a VR device mainly because it is not a see-through screen. But then there is this crazy advancement in which they can actually put this 4K screen so you see as it was see-through. So I believe, yes, it could probably, these algorithms could probably go there. For many applications, for instance, I think daily life, you really want to have see-through. So that's more appropriate. But we are developing algorithms which can be brought there. We have been working a lot with Microsoft HoloLens 2 because this is one of the most mature products so far when it comes to augmented reality. But this can virtually be brought everywhere.
Also, if I go like that,
yes,
museum, it can just help me, like...
We have, so Nairobi, we have it on smartphone, tablets, and wearable device, and it's the same technologies, just different implementations.
Okay, great. More questions, please. Okay, so thank you again.
Thank you.
So we'll take a 5 minutes recess and go on. This Zoom link is down. I don't know why.
Oh.
For you. For me, it's not, I don't know. The full name.
Sì, sì, sì. La teoria è uguale. Sì, 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 perché sì, sì, sì. Fantastico. Sì, da noi abbiamo preso il primo passato, abbiamo lavorato su qualcosa su retail, abbiamo fatto qualcosa così. Bella l'idea di fare una ricerca, diciamo, fondamentale, che poi già la pezzi con le application, però è fondamentale. E prima l'abbiamo scritto un po' così, nel senso che per noi facciamo con i CP, l'idea è fare una cosa fondamentale e poi magari fare un piccolo pilot, scriverlo per mettere sui dati di dominio e quindi noi quando spin-off, se riusciamo a fare una cosa che funziona e a wearable devices, anche mobile, però wearable è il senso. Ok, benissimo. Over research line that modifications. But we are on the other side, so we don't know much about partners. So our experience there was the theory of the platform was, but there what we saw is that we tried to use some algorithms since you also it doesn't. We have a robot, but it doesn't translate very well. So these algorithms don't translate very well as they are. I think it's also part, yeah, probably that, but it's also part of the story is that in ego-centric vision you have this anyway, you have this passive viewpoint where you don't really have to control the robot from moving. But so even if you do not localize yourself very well, do not navigate very well, if you say versus to this rate, but they're not supposed to do, they're not going to crash. In the case of robots, instead you need to be very precise. So that's why what we have at the moment is essentially does not translate very well there. We have another mic which is more based on geometry and it's more with support of the sensors like LiDAR. So we found out that like robotics for our experience, you don't have all those sensors.
Shall we start?
It doesn't generally
Yeah.
work.
Ready to go.
Yeah.
So I have my microphone open,
Yeah.
right?
Yeah. This is the mic, and I think everything is connected. So I have to just.
I send you the presentation.
Yeah. I hold it down. Everything is written. Okay. So
It's
now,
very short.
yeah. Now we move to our third presentation where Professor Emanuele Fontoni. Professor Fontoni is the full professor of computer science at the University of Macaretta and a co-director of the RetailVision Robotics and Artificial Intelligence Lab. Research interests include computer vision and artificial intelligence application in retail, robotics, video analysis, and human behavior analysis.
Thank you. Thank you, everybody. Thank you for organizing this workshop. I think it's the 4th year, so you are going on from quite a long time. And I see someone also connected online that was one of the founders of this workshop. I'm happy to be here, and I'm also happy to be here after the presentation of Antonino, because we have some connection that I think you will see more clear at the end of my talk. I'm guiding a research lab that is coming from several years of experience in the retail area, and mainly this quite big group of researchers is strongly involved with a lot of big companies around the world, going from the grocery retail to the fashion area that, you know, for Italy is a very crucial point where we are building a lot of application. So what I will try to do is to give you a short recap of 10 years of experience in this area, trying to get together a little bit more with respect to the past, the online with the offline. And then I will try to design a new research vision that we are discussing in this period, and I will go inside 2-3 different examples on this new research video. You will see several color codes. So when you see the red dots, that means that there is something new that is going on in this area, and I will tell you more on that. So we started really almost 10 years ago with this idea of the Shopper Science Lab. For us, the Shopper Science Lab is a long list of flagship stores around the world that can be used to gather a huge amount of data. And this idea is inside the physical store. You know very well that when we talk about online, offline retail, and when we go on the omni-channel challenge that we have today, the bad part of the story is inside the physical store, because there are still a huge amount of challenges. And that's why we need the help of very big brands. We have done a huge amount of projects with Procter & Gamble, with the GfK from Germany, with Luxottica also here in the US, in Canada, and with Huawei mainly for the phone market. And every time that you are inside the physical store, you are in a long list of troubles. You need to install cameras. Antonino was telling something about this. Usually the camera that you install is not the right one, is not having the full vision. You have operators in the middle. You have a lot of people that are not customers, that are doing a huge amount of things during the day. But even if we try to merge a little bit more the online and offline, we still have the same problems and the same challenges. So again, even if we are in 2023 and we are here discussing about generative AI and deep learning and AI, we are still very, very basic problems. So when you go in front of a shelf, sometimes you are not able to find the product that you need. And we call this shelf out of stock, SOS. But also, this is my story. A couple of weeks ago, you can receive a very nice email with the promo code. They know everything about you. They know the size of your shoes, everything. You click, you go inside, and your very nice shoes is out of stock again. And you cannot buy. And when there is nothing on the shelf, like in the picture, you cannot buy something. And why I'm telling this story? Because even if we are discussing about omnichannel retailing from, again, I think a decade, we are still far away. And that's why you see the red dots there. So when we go in the discussion of omnichannel, we are still considering the different channel, mainly like multi-channel than area omnichannel. And this is also, if we look back to the story of my lab, this is the same story. So we try to put all our research in this field in offline, online graph, and also on AI and generative AI. Okay, just to give an overview on what we are doing. But if you look, and no one is connected. Every research that we have done in the last 10 years is usually done in a sort of single shot without any kind of connection, mainly without connecting data between online and offline, without having the idea of using the same data sets, without having a common vision on omnichannel retailing. And that's why today I will try to give what is our future vision, also to invite some of you that are active in this field to cooperate on this kind of research. So this is our old vision. So when we go and we try to redefine a little bit what will be our future vision, this is what we are thinking about. And you see also that on the right part, there are a long list of red dots. And this long list of red dots has 3-4 main concepts. First of all, we want to try more and more to design common data sets and framework that are working really putting together the online and offline concept and data and algorithms to work with. And I will try to explain a little bit more. Also, we want to push a lot on the shopper science market. I will move it with my mouse here. This idea of the shopper science lab that I was showing in the beginning is the crucial point for us also to join again together the online and the offline. And if we go back to the ecosystem, to the name of the brands that we have the pleasure to work with, we want to push them also in this direction. And finally, one of the big problems that we saw in the last years and also during the COVID period is that usually our partners and mainly the companies that have to use our data and to make some actionable activities and to derive some actionable insights usually are looking to a dashboard and then taking a sort of decision that usually is also far away from what the dashboard is suggesting. So what we are trying to push here is to moving from a decision support system with a lot of dashboards. I will show you something again also on this side, to something that is very near to the final decision. We are calling this a sort of prompt-based decision following the trend of the prompt engineering for the generative AI. So we want to make a very new and simple approach on helping retailers to do the online and offline market altogether. So that's the main vision. Now going back very fast. We were almost the first to understand and to analyze interaction between humans and shelves. And this is our shopper analytics system. Is part of our story, and every shopper science lab has this kind of analysis inside. So we have a top view camera, you see there, I think you know very well this kind of application. There are 3 different neural networks that are able to understand who is passing by, the kind of interaction, and the amount of time. Now we are also doing something more strange, and I will introduce it in a few minutes. The same things is also designed for the vending machine. So for several years, we had this very nice vending shopper science lab that was around Italy. And again, it was a way of collecting data all together with the different location and the full access to human behavior analysis and to sellout data and to planogram and to category management, to all the different stories that we can decide inside the retail application. And for the vending machine, we adapt the same story. We can understand how many people are passing by, how much time they are spending in front of the vending, what is the gender, the age, the sentiment. We are using both frontal camera and top view cameras. And we were publishing a lot, also giving back data to Ferrero, for example, that is a big player in Italy that you know very well. And all this kind of information are used also as a test store when you have to design a new product and you want to put on the market a new product. You usually come to us, we make some tests together, and then you roll out this system. Okay, this is the story. Now, going on the technical side, we decided in the different years this kind of framework that we call VRINet, and we published a lot of papers on that, and you can find a full vision on that in a paper on machine vision and applications that is quite recent, but the approach that you see there are quite old in terms of novelties, but at the time they were very, very nice and interesting. The shopper analytics one is the one we discussed. Okay, we are able to understand the amount and the type of the interaction. The most precious data here are the negative interaction. I'm taking something from the shelf I'm looking at, and then I'm putting them back. Okay, and this has a lot of connection with what Antonino was saying about a different point of view in this kind of area. We have also a lot of public data sets in this field. If you want to use the data sets, this is a huge amount of pictures of ants entering a shelf and exiting a shelf with different SKUs on his ends. And if we move on, we also designed given this setup of a top view camera was quite easy to perform identification. So without covering the full store, we can understand if a customer is going on the beer and then on the diapers and then on the fresco fridge. Okay, totally based on identification. Again, you have a nice data set. There are 2 of them that are publicly available, and you can have a look on them and make a lot of assumption. Again, we published, we made some novel approach, also trying to put together temporal multimodal neural network for personal identification. It was one of the first trial in this kind of approach. And again, you can find a nice paper on pattern recognition letter from my team. The other point is that we tried also using this kind of configuration in an open world personal identification framework that was part of another publication that you can find here, and that is nice because usually when you want to have a look to the retailers that are in an entire city, you want to understand better who is coming from the store A only to buy diapers and then back to the store B only to buy drink and beers. Okay, and this is quite useful when you go to a brand and you ask for making a test together, because this is a crucial point. We usually in the last 10 years went to a big brand like Procter & Gamble or like Ferrero and asked them to perform some tests together, because only with this end user in the middle you can understand a lot about the way of doing. This is one of the last funny thing coming from the past, that was a weight estimator, again using the top view camera. Why we need weight? Because Ferrero wanted to understand better healthy versus not healthy. Okay, so I'm totally not healthy and she's very healthy, so it's very easy when you have a top view configuration to make it to afford this kind of classification and to give back to Ferrero a weight estimation with a sort of healthy novelty classification. The goal is always to perform customer segmentation, is the same that we are full of when we are online, but it's very, very hard when we are offline. And finally, the other point for our quite long history, was to understand what is on the shelf. So planogram management is another one of the pipelines that we developed in the last 3 years. Now this pipeline is very, we have a huge performances coming from a novel segmentation approach, and you know very well the state of the art. This is what is coming out. So you have the shelf, a picture coming from the shelf. This picture can come from a fixed camera that are in the shelf in front of this one, or can come from a mobile app like this one. Okay, and this idea of mobile app, because we cannot in the real retail afford 1,000 of different cameras everywhere, is a point that Antonino already discussed. When you saw a dashboard like this kind of solution is also trying to start the process of telling you something new. What is the something new here? Is I have a couple of very typical out of stock in the Pampers Baby Dry 4 and Pampers Baby Dry 3. My suggestion is to give one more facing to this kind of SKUs so that you can try to avoid out of stock. And this solution is probably was probably one of the first prototype that was going on the direction of having something that was totally new. And again, going back to our vision, it's very, I hope that is now more clear that we had a lot of green dots always performing analysis, but we had very few orange or red dots that were really suggesting a solution. And when you are discussing with a store manager or with a category manager, you cannot think that they are totally able to read between your 1,000 data that you provide with 10,000 dashboards and then to find the correct solution. That's why we try to push a little bit, mainly focusing on the generative AI, and then we come back to the huge amount of data that we collected in the past to try to understand, okay, let's start from the trajectories, because we know there is a lot of research, there is a very nice state of the art in this field. So the question was, can we predict and generate and simulate the flow of the customers in a given period, in a given store, and are we able to make a generalization on that? And we started from here. And I think again that today we will have several points of view on this kind of solution. We have and this is again a public data set that you can use, a large trajectory data set for human behavior understanding. And these kind of trajectories are always coming from cameras. We are a partnership with Sovis, and we are collecting a huge amount of trajectory, mainly in Europe and US. You see the numbers, okay? Millions of people that are centimeter by centimeter tracked inside the store. But the problem here is that we have different stores, and we started making a lot of research here in this kind of topic, also comparing some traditional trajectory-based data set with some retail specialized trajectory-based data sets. This is probably one of our best paper in the last years. You can find this on path recognition, and we published this paper with three main contributions. The first one was on the data sets with the specialized retail data set only to show the ability to make generalization in different stores, because stores can be designed in a very different way. Mainly, we are talking about Edeka, Globus, Reve, Aldi. I don't know if you know these names, but are very famous retail chains in Europe and mainly in Germany. The other one are coming from the literature, and there is the ETH, the Zara 1, Zara 2. These are two fashion stores connected with Zara. And we also made a contribution on the metrics to try to perform a new way of understanding how we are able to generate human trajectories inside the store, and now we can evaluate human trajectories inside the store. The other part of the literature that is working here is the one about autonomous driving car that is trying to predict human trajectories for security reasons. And you can see here some of the results coming probably from a method again that is quite old with respect to the current state of the art, but the paper is from the 2022. And you can see that the predicted and generated trajectories are really, really nice, even if you can choose to go on the right, on the left, straight on. And also the results are still today the best that we can have on this kind of data sets, and there is no other paper that is overcoming this kind of results. But why I'm telling this story? Not because of these results that are part of the story of our history, but mainly because this is part of our new vision. So what is the new vision, and why we are always discussing about prompt-based decision support systems? Because this is one of the first trial of having a store simulator. So what we ask to this system, please generate 100 customers for the different clusters in this store design. We give the store design and we give the category placement. So we say, okay, this part is beer, this part is diapers, again, this part is milk. And we start seeing what happens to these quite real users. But why I call them quite real users? Because their trajectories inside the store are coming from the same trajectory generator that I was showing you before. And we only have a nice way of understanding with the store designers. Who are the final users of this application? Mainly, first of all, the store designers. The first step when I design the all over store. But secondly, week by week, category managers. People that have to decide where to put the secondary placement with the promo of the diapers, people that have to decide what they have to put on the gondola end, near to the exit or near to the cashier system. Okay, and they are the one that usually in the past go there, test something, have a look 2 or 3 weeks, then go there, test something different. And this is going on from, I think, decades, okay? And that's why we are pushing on this idea. The red dots is because this is something new that we are working on, and we are happy to cooperate on this kind of solution. The second part of the story is when we are not starting from the offline and from the real store, but when we are starting from the online. And on the online area, mainly for fashion brands, we are collecting today 80,000 images per hour coming from Instagram. And why we are doing this? Mainly to perform visual evaluation on Instagram images, visual trend analysis, and so on. Let me give you an examples on the bags. We do all the pipeline starting from the data acquisition. Then we classify, first of all, fashion with respect to no fashion with a very, very simple approach. Then we start giving different classes to the handbag detection, to the different classes of big bags, small bags, circular bags, and so on and so on and so on. We try to classify the dominant colors and cluster them. And then we add some different outputs, adding also geolocalization in this kind of output. If we want to go a little bit more in details, this is the object detection system that is able to understand that this is a bag. Then we go inside the bag and we try to find the dominant color. Together with dominant color, we want to understand what is the function of this bag, if it's big or not, if there are metal accessories or not. And we are making a rich collection of data set. All this rich collection of data set brings to different applications, mainly designed for the online part of the story. And this part is starting from, for example, the geo style. You want to have a look on what happened on Instagram the last week in Tokyo. So you select something, or here we selected the United Kingdom, and we have a sort of summary of the most relevant picture. When we say relevant, we also, during the different pipeline of classification, we can give back a sort of novelty score of the different images that we see, just to avoid to show you 10,000 images always of the same contents. And then we started to push this test with some of the brands of the fashion, of the world fashion brands that you saw in my slide in the beginning, to try to understand if the trends that we are gathering from the social media are in line with your sellout data. So this week, the last 2 weeks, red bags with metal details were going very, very strong, and the trend was very, very positive, while my sellout is totally in the opposite side. Why we are doing this? Because usually when this happens, that means that we have some out of stock somewhere on our supply chain. That means that even if everyone is discussing about red bags, probably you have no red bags on the stores, or you have no red bags on the online, or you have no promo for the red bags on your communication activities. And this is a big problem, because if you are looking to the Instagram to understand trends, and then you are not able to follow this trend with your real supply chain, you are getting in trouble. And then you have also different kind of a comparison. You can have what is going on about color, shape, and accessories on the social media, and what is going on about this kind of stuff on your sellout data. And to tell you a little bit more about our experiences, the other point in our story is to trust a lot on retailers. You see here, the example is the one of My Teresa. And if you go there and perform some web scraping over there, you can collect a lot of images from different brands. And together with these images, if you trust on the description, now we are able to collect a lot of labels. We are not making segmentation on this kind of data that we collect, but we have a lot of automatically labeled data that are coming from these retailers. In a certain way, we are trusting on everything that they describe, and we are using the images that we are scraping from these retailers. There are quite a lot of them, very, very famous in the fashion trend, in the fashion area, that are My Teresa, Farfetch, Net-a-Porter, but also you can trust a lot of the brand. You can go on Gucci, on Prada, on Fendi, and you can download a lot of images with quite trustable labels for our classification purposes. Starting from here, we are also giving back to our customer and to our partners a nice dashboard with a lot of suggestion about collection and assortment. So what we are saying is, guys, look, your competitor is having 25 bags on the price level of 1,000 euros. And of these 25 bags, 12 of them are red, and you are totally on the different sides. You have different bags, even if you are competing on the same market with the same level of products. And this idea of also taking a lot of images inside the dashboards and a lot of images inside the suggestion that we can give was the images that inspired one of the new red dots on my presentation. And so going back to my view now, I will try to go to the conclusions, showing you some of the ongoing researches that we are focusing on that are totally going on the direction on giving back to our partners a very easy way to use our data and to find an applicable solution, an actionable insight. So if we look to Collection Grid, what you see here is a web interface where we are suggesting a sort of collection grid. What I mean with the suggesting is a sort of collection grid. We are generating a mix of products with different subcategories, different price levels that are following a mix of trends that are coming from your sellout in the real store and what is happening on the social media and what is happening on the retailers. And this kind of a grid of collection grids, so we call this kind of solution collection grid, is no more a real dashboard. So it's no more something that I have to read, to understand, and then to use to make the actionable decision that I have to perform. But it's something that is very near to the final decision. And you know that given this huge amount of data, and this is coming from a CVPR paper of the last year, giving this huge amount of data, we can also start reusing all the generative AI approach to suggest a new way of making human AI cooperation on the creativity field. Okay, these small videos are totally generated. You can go back in the CVPR 2022 paper that we use it as a base for this. But we are not saying, okay, this is a suggestion for your creativity. But again, we are saying this is a summary on what happened in the last week on Instagram, because the fine-tuned part of this approach was based on the data collected in the last week on Instagram. And if we want to move on also here to follow the red dots, we can try to design something, and I always use the example of the bags that can help you during your creativity phase. And what you see on the right is a very easy to use and easy to manage Telegram bot. So you take a snapshot, you are drafting something on the paper, you take a snapshot with your mobile, you send a snapshot to a Telegram bot, and this system is giving you back a nice texture, a nice materials, a nice mix of colors that is coming back and mixing together the data that are gathered from the social media. Okay, nothing special is in terms of approach that is behind, but this system that we call a style trend gun is very precious because it's mixing online, offline, and creativity support in the same content. And for us, up to our knowledge, there is not so many things that are using and mixing this huge amount of data. And the same story can be then applied to the planogram. And again, I don't want to have only an analysis, but I want to have a final solution. So I can ask, I need a planogram for a pet food category with the 1.33 meters of shelf on 8 levels. The average visitors paid per day is 400. And the max shelf out of stock that I can allow is the 3%. The central lines go to Mars. Okay, you know, it's a big brand producing chocolate and pet foods. We can discuss about this, but they are doing this. And the solution, the system is giving you the optimized planogram for this kind of request. And you are no more passing by a human for the interpretation, but you are using a lot of human brain for the prompt design, for the prompt engineering part. And if you read this back on the recent trends on all the generative AI approach, this is something that we really want to work on. And finally, if we go again back to my Teresa and to the example of the newsletter that I received with no production stock, I can ask, please provide a design and contents for the Italian market homepage based on the last week traffic data with the max stock level of 8% for promos and the minimum turnover for Fendi of 8 key euros per day. What I'm saying, I'm suggesting a sort of scenario, and the system is helping me to design what kind of, it's not designing nothing, it's only deciding what kind of products will be on the page, what kind of promo you can suggest to do, given this kind of scenario that we want to follow. And this idea of prompt-based design applied to several retail applications is one of the vision that I was trying to tell you during my presentation. Now, going really to the conclusion, what is our experience in the real store? That, again, Antonio discussed at this point very, very well. Again, the challenges are all there. Nothing changed. Even if we have a huge amount of technology, we still have the problem on where we need to install our camera. And this is a huge problem in the physical retail, because you see here some pictures, they are totally different. Sometimes the only one power cable that you can find is somewhere in the ceiling, and you find here a very funny solution. The picture that they found here in the US with cameras, with an RGB cameras that was probably also quite dangerous for people passing there. So what can be the idea to cover this gap? Because the gap between online, offline, and offline is tremendous. That's why probably brands like Procter & Gamble or Ferrero or Fendi are not using this couple of data together, because they are not collecting with the same easy way data from the online store, from the real store, from the physical store. And that's why probably, and is also what is our vision here, probably we will use the same story that Antonino was telling before. So we have this idea of a first-person view, of a egocentric view, call as you want, but probably is not on every customer for sure, but will be mainly on the operators. And Agostino, together with Marina, designed a nice Italian project on this kind of view, putting together fundamental research with a nice way of applying them. The other one is the connection that we have with the PAL Robotics. This is a quite famous European brands in the mobile robotics. And we are now working together to put all the cameras that we need inside the robot that is moving around, because it's almost impossible to have cameras everywhere in every store for every need. So this is our part of the story, going back from several years with some new views and with the idea that we are very happy to cooperate with all of you. Thank you very much.
With the plan, what's the plan?
Planogram management.
Planogram.
Yeah.
And what degree does like dollars spent? How do you incorporate that?
You mean dollars spent?
Yeah, so you've got the agents.
Yeah.
Do you pay actually, points of sale data? Is that?
Yeah, no, we totally incorporate this kind of
How
data.
does that?
Just to give you an idea, when you go in front of a shelf, when you see that the Pampers Baby Dry for, okay, I'm a kid expert for 10 years with diaper sensitive kids, the real one. When you see that you have 4 facings of the same SKU, of the same product, this is because of the sellout. You know that probably this is a high rotating product with the high sellout. So to try to be more robust with respect to out of stock, you are integrating this kind of solution in the optimization. We have a nice paper on computer industry that is based on the design of this optimal system that is integrating not only the sellout, but you saw on the prompt there is a sellout, people passing by, because the design of a shelf totally depends on the amount of people that are passing there. That is depending also on the sellout. And then how you move the single SKU. What I mean how you move.
When you have something that is not touched at all, you start trying to move this kind of solution in this kind of product in the center. The center is usually occupied by big brands. If you are on diapers, Pampers is there. If you are on cereals, Kellogg's is there. Okay. So we start moving this. When I say we start, is the algorithm is suggesting you to move this product somewhere else. Then, if this product is again not touched, not buy, because we are not saying only buy, because touching is probably something nice. Then I can make a promo price, and you will see that someone will buy this. This way of moving is part of this paper on computer in industry. And if you write me something, I will share with you. The idea of optimizing planogram in a very scientific approach is still far away from the reality. So everyone is discussing about, but no one is applying.
So how do you usually get the 3D model and floor plan of the store?
Now it's quite easy, because you have year to year, they're discussing about easy and fast way to design 3D models. And the first approach is using a LiDAR-based solution, a commercial one, okay? When you need a 3D. You almost never need the 3D model. So we only, everything that you saw here is based on a single picture of the shelf, frontal picture of the shelf, and a top view of the store. Okay. When we need the 3D model of the store, when we have the robotics inside, so we need a sort of map that is quite accurate to put the PAL robotic system inside the store.
And the other question, when you have, the user with the cell phone or, the first view going to the store, you never have the perpendicular.
This is totally fixed on based on classical computer vision approaches. Why is easy? Because you know very well the shape of the single SKU that is on the shelf, and so you are totally able to rectify the image to perform all the geometric approaches on the vision part. Still no. This is something that I'm interested in doing some test. Why I'm telling this and why I'm pushing on the real world application. So for me, the way of doing is go there, send an email to them, and convince one of these to perform a test together with us. Okay. This is the only way in the last 10 years I use it to understand if we are doing something that is really useful for someone. But then as a research team, we are doing a lot of fundamental research. But this is a different story. Your fundamental research goes on pattern recognition, on CVPR, and we are very happy. But then we have to look to someone that is also helping us, because when you have to collect 3,000 images and label them, we don't want to have slaves in our lab, and we trust on the slaves coming from the companies.
I chuckled because work with some of these brands, an experience I have is that sense of success working, doing research, working with, commercial partners. Something I've observed is brands will be interested to collaborate on primary research. It's nice, it demos well, it shows innovation, but actually getting to like widespread adoption, like proper rollout, there's this gap in it.
A huge gap.
Have you had any,
Yep.
thoughts on that?
Give me Jeff.
Stories where you have gone from a POC that's been successful. I'm sure you've got lots of successful POCs. What are the ones when it goes to production?
Totally agree on that. So our story is part of what you're saying. So we had a lot of successful POC, but a few rollouts. For us, the successful story is the shopper analytics for Procter & Gamble that now are installed in China, Indonesia, Europe, and US. And with this idea, we designed, we founded the spin-off, and then a company in Italy bought this spin-off company to go on the market with this solution. And now the company is going on very well, no problems. The other new rollout that is coming out is from Mars on the shelf management. Now we are collecting 30,000 images from something like 1,600 stores in Europe, and they are going with their own workforce, probably are vending, what is the name, commercial guys that are going around, and they are in charge of taking the picture of the shelf. And with this huge amount of data, now we are performing some new ideas, going on the direction that you were suggesting, but also on the prompt-based generation. Because if you go to Mars, even if it's a very, very big company, and you show them 15 different dashboards with a lot of information inside, they say, nice, very nice. You come back after 1 month, no one is opening the dashboard. No one at all, even if they are data scientists, not commercial guys. But you are totally right. So we have some nice stories, but are the 2% of the POC.
If you could say, was there anything that what's the differentiator, what made those successful? Like human relationships? Or
no, totally the easy way to have actionable actions after you collect the data. When the problem is too much complex, they have to think too much or to use too many data to take a complex decision, no one will perform a rollout. When the application is very near to the decision, they will perform a rollout. That's why our red dots are all on the idea of being very, very near to the final decision. So you write something and I give you a quite nice solution. Is the best one? Is the optimal one? Not at all. But is a proper solution better than the one that we are doing mainly based on impression and not on data?
Thank you very much.
Thank you all.
Okay, so we'll take a 10 minutes recess and then we have our two last.